Hello everyone. Today I'm going to cover 3 sections in our calculus, 2 course sections 11.5, 11.6 and 11.7. We will continue talking about type of series. I'll show you new type of series and the more tests for convergence. So let's start with 11.5. It's about alternating series. Okay. 11.5 alternating series. Okay. So the name says alternating series is a series of the sign of the terms going to be alternating or going to be changing. So the definition is alternating series, sum of -1 raised to the n of an, okay, and from 0 to infinity. And this means what? First term is n to the 0. Now I start from 0, right? So -1 to the 0 is 1. So this is a to the 0, right this way. So a to the n, down, not up. You know, some books right up there, but it's going to get confusing with the exponent. So we stick to our books, which is better. And down here, so this means what? A 0, and then what? When n equal to 1, -1 to the 1 is a negative. So minus a1 and plus a2 minus a3 plus a4 minus a5 plus da da da. So you see what? The terms are changing, right? A0 minus plus minus plus minus in this type of series because alternating series. The -1 to the ends right here is just a technical way of expressing the sign of change, right? Because -1 raised to even exponent going to give you a positive number. Odd exponent give you negative, right? By the way, some other books you see, you may see in the homework. Instead of using -1 to the end, you may see this. Cosine, n pi times an, okay? And this is another way of showing you the alternating sign when n runs from 0 to infinity. You see why? Because what? When n equals 0, cosine of 0 is 1, n equal to 1, cosine of pi is going to be -1. So it's just another way, another fun way to express the alternating signs, okay, from positive to negative. Those are equivalent. Those are the same. All right. What if you want to start your series? Start with 1. Then I can write this way: sum a sub n. Oh, I better write out here. A sub n. N run from 1 to infinity. So I have what? A1 minus A2 plus A3 minus A4 plus A5 minus da da da. This is also alternating series, but now be careful with the alternating sign. -1. Now I cannot raise to the n anymore. Why? Because if I got n equal to 1 to start with, -1 to the 1 is going to be a negative and minus and plus. But this one that way, so I'm going to raise to the n plus 1. Because what? When n equal to 1, this is -1 to the 1 plus 1, which is 2. So -1 squared is going to be positive. Now things back to normal. So either way. That's why I claim that many people prefer this because it's only exponent n and nothing wrong start with 0. Okay? Our book right this way, so I show you this as well. So those are called the alternating series, where just series where the term is just keep adding and subtracting alternatingly. Okay, now let me give you an example. Sum of -1 raised to the n plus 1, okay, n sum from 1 to infinity of 1 over n. And this is actually this 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1 over 6 plus da da da. Okay. How about this? Sum n equal to 1 to infinity, -1 raised to the n of 1 over n squared. This is what? 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus 1 over 5 squared minus 1 over 6 squared plus da da da. Okay? You see it's kind of P series in here, right? And here P equal to 1, here P equal to 2. Now we change the signs, so those are alternating series. Okay, now let me show you the test for alternating series. So let me write in general. They call alternating series test. Alternating series test. So this will answer the main question. How do we know if an alternating series is convergent or divergent? So in general, you have an alternating series, -1 to the n. Let me write this in the book way. So how about n plus 1 of an ends from 1 to infinity. This is your alternating series, which is a1 minus a2 plus a3 minus a4 plus da da da. Okay? And here is the condition. An is positive, greater than or equal to 0 for all n. We don't need that anymore because we indicate a negative positive sign already. Actually, yeah, we need that. Yeah, we should need that. Okay, if it's negative, then it's back to positive. So it's positive. Okay, an is positive, and what else? Decreasing. So an plus 1 gonna be less than or equal to an. So the next term gonna be smaller. So just say 1/2 is bigger than 1/3, or 1/3 less than 1/2, and 1/4 less than 1/3, so on and so on. Okay, keep adding and subtracting a smaller number. That's what it's trying to say. And if the limit of an when n approaches infinity is equal to 0, so all three conditions happens, and you can say that the series is convergent. The alternating series convergent. I'm showing you the test right here saying what? You have an alternating series, okay, that satisfies three conditions. All the terms are here, ignoring the sign, okay, plus or minus. All the terms, all the numbers are positive, and the next term is going to be less than the previous term, and the limit of the n term equal to 0, then the series is convergent. So actually, those two alternating series right here are convergent. You see why? But the first one right here, let me show you. First example right here, an is equal to 1 over n, right? And is that positive? Yeah. Because n is 1, 2, 3, 4, 5, positive, right? An plus 1 is equal to 1 over n plus 1 is actually smaller than an, equal to 1 over n, because you have the same numerator, bigger denominator, give you smaller fraction. So the second condition, check. The third one, limit of 1 over n, when n go to infinity, that's equal to 0. You take n get bigger, 1 over infinity is 0. So all three conditions happen. This series is convergent. Okay. And the second example right here, pretty similar. This is square. This is square. And this is square. Of course, same idea. Square is equal to 0. So the second series is also convergent as well. So for alternating series, is the sign changing? You want to test for convergent or divergent. If the series satisfies three conditions, then you can use the alternating series test to see if it's convergent or divergent. And after knowing that the series is, say, convergent, the next question will be, how do I find the sum? Okay, add them up. What is convergent? 2. The answer is I don't know, but at least I can approximate. Okay, so how do I approximate? We use partial sum as we learned before. So the sum here, say the sum is S, okay? S is approximately equal to Sn. Because what we mean by Sn, the sum of the first n term, okay? S is what? The sum of all the term. And if it's too hard to find the sum of all the term, well, I can approximate using the sum of like 1,000 term, for example. So n is 1,000, a million term. That would be good enough, more than good enough, more than enough to approximate the sum of the S. So this is how you approximate. And if you approximate, then you're gonna make some errors. And how to estimate the errors. Okay, I'll try to use the right words the book uses. Use right notation. The book uses R for errors. So, E for error. R is this. I think it's for remainder. This is the errors. Okay, is the difference between the actual sum and your approximation. See? Our book uses R, but I use E. E stands for errors. But I'll try to use the same notation in the books. Okay, Rn is the remainder, I think that's how they call it. It's equal to the difference between your actual sum and your approximation. And this is no more than An. I think it's An plus 1. Let me double check on it. Yes. Okay? So if you use 5 terms, 1, 2, 3, 4, 5 terms to approximate the sum, then your errors is no more than 1 over 6. Okay? So in here, in this sum right here, you use 5 terms, 1, 2, 3, 4, 5 terms to approximate, then your errors is no more than 1 over 6 squared. That was the idea of the main point of the remainder in here, the errors that you may have when you approximate the sum using n terms. So what if I use 100 terms? Then my approximation is going to be what? 1 minus 1/2 plus 1/3 minus 1/4 all the way to 1 over 100. And the errors is going to be no more than 1 over 101. In this example right here, the error is going to be no more than 1 over 101 squared if you use a 100 term, that's 100, to approximate the sum. So the point is what? The more terms you use to approximate the sum, the smaller the error you're going to make. Okay? And this is the end of the alternating series. Keep those 2 examples with you because when we move on to the next section, I'm going to come back to those examples. Next section, I'll be talking about absolute convergence. And I'm going to show you 2 more tests, the ratio test and the root test. And I claim that the 2 tests, the ratio test and the root test, are equivalent to each other. Means what? Whatever happened to the ratio test is going to happen the same way to the root test. Okay, you won't expect a different result if you change the test. And let's see, 11.6. Okay, 0.6. Absolute convergence ratio test and root test. Okay. So first of all, let me talk about absolute convergence. We have a series, An in general, right? Say n run from 1 to infinity. This is how our book denote a series. So we start from 1 most of the time. So this means what? A1 plus A2 plus A3 plus A4 plus da da da. Okay. And we have another series. Absolute value of An. N run from 1 to infinity. And this series means what? Absolute value of A1 plus absolute value of A2 plus absolute value of A3 plus absolute value of A4 plus da da da. And this is the absolute value terms of the previous series. Okay. So for the first, the previous one right here, the first one right here, the first series right here, the A1, A2, A3, some of those could be positive, could be negative number. It may be the alternating series, maybe not. So you got A1 plus A2 minus A3 minus A4 plus A5 plus A6 minus A7. Okay, could be positive and negative somewhere around. Don't need to be alternating. Okay. Now we want to make all the terms positive, and we introduce a new series. Okay, and I'm not sure about the name of this, but let's call it the absolute value terms series. Okay, so all the terms that we put the absolute value around, so all the terms are positive. So I'm pretty sure that this sum is going to be a positive number. Okay, well, make it this way, non-negative number. If all the terms are 0, then add up 0. But usually, most of the time, it's going to be a positive term. So you add all the absolute value terms together, you're going to get a positive number. Okay. Now we're going to talk about conversion of those series. I need some room to write. I'll write too big right here, so let me try to write small. If the sum of An absolute value is convergent, and the sum of An, no absolute value, is also convergent, is convergent as well, then we say that this one, okay, is absolute. Is an absolute conversion series. Is an absolute conversion series. Okay, so this absolute series conversion and the original conversion, then we say that the original series is absolute conversion. So highlight this. Okay, absolute conversion. Another one, if the sum of the ends is convergent, but the sum of an without the absolute value is divergent. Oh, I wrote it backward. This is divergent, but this is convergence. Okay. And then the series is called what? Conditional conversion series is a conditional convergence series. Okay. So we have two cases in here in a nutshell. The original series is convergent, but the absolute value term series right here could be convergent, could be divergent. It depends on the case. We can call the original series an absolute conversion or conditional conversion. Okay, this series is convergent. First of all, this one could be convergent or divergent. That's the second thing. This conversion and that conversion, and we say what? Absolute convergence series, or the original one. This conversion, this is divergent, and we say the original series is a conditional conversion. Okay. Alright, so usually I don't write that much, it's just a lecture, but when I say it, I'll do it this way. Let me try to make it short. Sum ANs converse and sum of absolute AN converse, then we say that sum ANs is absolute and converse. Okay? And now the second one, sum of ANs is conversion, but AN is divergent. Then we say what? Sum of AN is still convergent, but say what? Conditional is convergent. Okay? So that's how I have in my mind. We have to write more and make it looks like the way the book write. Okay? In short, that's what we need to know. Okay, so let me show you an example of series absolute conversion and conditional conversion. The first one, sum of -1 raised to the n plus 1, 1 over n run from 1 to infinity. And this is what? 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. Say 1/5 plus da 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 da. Okay? And you know that this series conversion already. We're using the alternating series test we just learned on the previous section, 11.5. Okay? But the actual value of this, sum of -1 raised to the n plus 1 over n, and the actual value, this is really 1 plus 1/2 plus 1/3 plus 1/4. You recognize right away this is a harmonic series, and this is divergent. And this is convergent. Okay? So this series is together, we say that what? Our alternating series is conditionally convergent. Okay? -1 to the n plus 1, 1 over n, and 1 to infinity is conditionally convergent. This is conditional. Okay? It is convergent, but its absolute value series is divergent, and it's just convergent conditionally. Okay. Second example, when I change this to this square, I have square, square, square. It's convergent, and this one is what? Square, 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 so forth. And you see that which we learned before as well. This is the P series with P equal to 2, and this is convergent as well. So the original series convergent, and the absolute is also convergent, and we say that the original series is absolutely convergent. Okay. So we learned two types of convergent of a series. If the original series is convergent, okay, first of all, and we put the absolute value is also convergent, then we have a stronger statement. The original series not just convergent, it is absolute convergent. Okay. The second term is that the original series is convergent always, but when you put the absolute value around, it's divergent, not convergent anymore. Then we say that the original series is only conditionally convergent. Okay. And that is about the absolute value convergent. This is the concept. Okay. Now let me show you two more tests called the root test and the ratio test. And one more time, I claim that the ratio test and the root test are equivalent. That means if you cannot get the result from the root test, you don't need to try the ratio test because you cannot get the result either. Okay? Given that your algebra is good, it's perfect, then you don't make any mistake. And why do we have two tests? It's because it depends on the nature of the series, and sometimes the root test is easier, some other time the ratio test is easier. It depends on, again, depends on your algebra skill and the type of the series that you have. Let me first of all say the test, and now I'm going to give you some examples. Okay. So we have a series. First of all, ratio test. Okay. Ratio test. First of all, we have a series an, okay, n equal to 1 to infinity, which is a1 plus a2 plus a3 plus a4 plus da da da. Okay. What we're going to do here is we're going to calculate the limit of an plus 1 over an. Take the absolute value, so make sure it's always positive. Okay. So what we do in here, we take the next term divided by the previous term and take the limit for n go to infinity. And this is equal to some limit L. L could be a constant, could be infinity. Okay. Now we have three cases. If L is less than 1, L is less than 1, then the series right here is absolutely convergent. Okay. If L is bigger than 1, then it's going to be divergent. We only have one type of divergent, guys. Divergent means the sum equal to infinity or the sum is undefined. We don't have absolute divergent because when I teach Calc 2, people just ask for that, but just divergent, okay? And where L is equal to 1, then we have no idea. Be professional and inconclusive. So we don't know whether the series is convergent or divergent. Alright? So the idea for ratio test is what? You're gonna take the ratio, okay, the fraction from the next term over the previous term, and you calculate the limit when n goes to infinity. The following three cases, if that value is less than 1, of course it's going to be positive because absolute value, okay? But less than 1, and you know that the series is not just convergent, it is absolute convergent, okay? So this test is pretty strong. It tests for absolute convergent, okay? And if the limit is bigger than 1, then the series is divergent. Bigger than 1 means the next term tends to be bigger than the previous term, like the ratio. And if it's equal to 1, then we have no idea. Sometimes it's convergent, sometimes it's divergent. No clue. And that means what? we want to test, we have to use a different test. We don't use ratio test, and we don't use a root test either. Later on I'll show you the root test, but because whatever happens to the root test is going to happen the exact same way to the ratio test. So you get a L equal to 1 for the root test, then the ratio test. You don't use the root test, and vice versa. Okay, that was the ratio test. And now let me show you the root test. Then I'm going to give you an example. Root test. You guys are going to see a similar version. You have a series as well. Now instead of making a ratio, we're going to